Hello and welcome everyone. This is Anil at my channel Math with AKS. Topic chosen for this class is complex numbers and quadratic equations. The first 12 questions are taken from KCET exam papers. First question is, if alpha and beta are two different complex numbers with modulus of beta is 1, now we need to find modulus of this expression. In solving this, we need to use the following results. So for any complex number z, the product of a complex number and its conjugate is square of the modulus of the complex number. In particular, if the modulus of the complex number is 1, then z into z bar becomes 1, and therefore conjugate of the complex number is reciprocal of the complex number. Whether z and z bar are reciprocals of each other. Also, we need to use this result. Conjugate of the sum of two complex numbers is sum of conjugates of individual complex numbers. And as we know, this modulus of z1, z2 is mod z1 and mod z2. Also, modulus of z1 upon z2 is mod z1 upon mod z2, provided the denominator not 0. Using these two results, we can get the results in the new form. Modulus of z power n is mod z whole power n, where n is any integer. So here modulus of this expression is same as modulus of the individual terms. We know that complex number into its conjugate is modulus of the complex number whole square. Since modulus of beta is 1, this becomes 1 square equal to 1. Therefore, beta into beta bar is 1. Now in the given expression, beta minus alpha upon 1 minus alpha bar beta, we shall replace 1 by beta into beta bar. Numerator will be as it is, beta to beta bar minus alpha bar into beta. Now in the denominator, we can take beta as a common factor. Beta bar minus alpha bar, numerator as it is. Now this can be written as modulus of beta minus alpha upon modulus of beta into modulus of beta bar minus alpha bar. Modulus of beta is 1, and we know that conjugate of z1 minus z2 is z1 bar minus z2 bar. Therefore, this can be written as modulus of beta minus alpha upon 1 into modulus of beta minus alpha whole conjugate. Since conjugate and the complex number have the same modulus, that is mod z is same as modulus of its conjugate, these two get cancelled. So you'll be left with 1 upon 1, that is 1. So the answer is first option 1. Second question is, if 1 omega omega square are the 3 cube roots of unity, then we need to find the value of this expression. First, we shall learn what omega means and what are the cube roots of unity. Square roots of unity is defined as the roots of the equation x square equal to 1 are called square roots of unity. So 1 and minus 1 are the square roots of unity. That means when you square these numbers, you get 1. 1 square is 1. Square of minus 1 is 1. In the same way, cube roots of unity are the roots of the equation x cube equal to 1. Solving x cube equal to 1, we get 3 roots, 1 omega omega square. X cube equal to 1 is a cubic equation. It will have 3 roots. So where omega is minus 1 plus I root 3 by 2 and omega square is minus 1 minus I root 3 by 2. Remember, omega square is the conjugate of omega. And remember this results. 1 plus omega square is 0. Sum of the cube roots of unity is 0. And omega being the root of x cube equal to 1, omega satisfies the equation x cube equal to 1. And therefore, we get omega cube equal to 1. Now, 1 minus omega plus omega square into 1 plus omega minus omega square. Since 1 plus omega square is 0, 1 plus omega square will be minus omega and 1 plus omega will be minus omega square. So here 1 plus omega square can be replaced by minus omega, and here 1 plus omega can be replaced by minus omega square. So this becomes minus omega into minus omega square minus omega square. That will be minus 2 omega into minus 2 omega square. That becomes 4 omega cube. Since omega cube is 1, you get 4. So the answer is the first option. Question number 3. If z is given by this expression, we need to find the modulus of z. So here we shall use these properties. Modulus of z1 into z2 is modulus of z1 into modulus of z2. And modulus of z power n is mod z whole power n. Also, modulus of the quotient z1 upon z2 is modulus of z1 upon modulus of z2, provided z2 is a non-zero complex number. So you can take this as modulus of z, modulus of root 3 plus I whole cube into modulus of 3I plus 4 whole square upon modulus of 8 plus 6I whole square. Remember, modulus of x plus or minus iy is root of x square plus y square. So we can write this as root of 3 plus 1 whole cube into root of 9 plus 16 whole square upon root of 64 plus 36 the whole square. That gives us root of 3 plus 1 is root 4, that is 2 cube into 25 upon 100. 25 4 the now 8 upon 4, that is 2. So the answer is second option 2. Next we shall take up this question, fourth question. Alpha and beta are the roots of this equation. Then alpha square plus beta square is equal to given equation x square minus ax plus b square equal to 0. This is of the form ax square plus bx plus c equal to 0. On comparing, you get a is 1, capital B is minus a, and capital C is b square. Since alpha and beta are the roots of the equation, sum of the roots alpha plus beta minus b upon a, that is minus of minus a upon 1, that is a, and product of the roots alpha into beta is c upon a. C is b square upon a is 1, b square. You can write this alpha square plus beta square as alpha plus beta whole square minus 2 times alpha beta. Now substitute for the sum, that is a square minus 2 times product alpha beta is b square. So a square minus 2b square, that is the fourth option, is the answer. Now, fifth question. In this, we are asked to simplify this expression in terms of I. I power n plus I power n plus 1 plus I power n plus 2 plus I power n plus 3. Here we shall use this law. A power m plus n can be written as a power m into a power n. Later, I square is minus 1. Here I power n as it is, we can write this as I power n into I power 1 plus I power n into I square plus I power n into I cube. Further, I power n can be taken as a common factor from each term. Then we get 1 plus I square plus I cube. So that is I power n times 1 plus I square is minus 1. I cube is minus I. Then you get I power n into 0. Get 0. Next question. To find the real part of this complex number 1 minus cos theta plus I sin theta whole power minus 1. Take that as z. That is 1 over 1 minus cos theta plus I sin theta. You can write this as 1 over 2 sin square theta by 2. That is 1 minus cos theta can be written as 2 sin square theta by 2, and sin theta can be written as 2 sin of theta by 2 into cos of theta by 2. So in this we can take 2 cos sin square theta or 2 sin theta by 2. 2 sine theta by 2 as a common factor. And then we will be left with sine of theta by 2 plus I times cos of theta by 2. Remember, reciprocal of sine theta plus I cos theta is sine theta minus I cos theta. So we can write this as sine of theta by 2 minus I cos of theta by 2 upon 2 sine of theta by 2. Divide each term by 2 sine theta by 2. Sine of theta by 2 upon 2 times sine of theta by 2 plus I times minus cos of theta by 2 upon 2 sine of theta by 2. That is 1 by 2 plus I times minus cot of theta by 2 upon 2. So the real part is 1 by 2. And this is the imaginary part. The answer is first option. If 1 plus I upon 1 minus I whole power m equal to 1, then the least positive integral value of m is, options are 3, 1, 4, 2. So here, in the usual method, we need to rationalize and express this complex number 1 plus I upon 1 minus I in the form a plus ib and then proceed with the problem. Instead, please remember this, 1 plus I upon 1 minus I is I, and 1 minus I upon 1 plus I is minus I. Easy to remember. In the numerator you have plus I, rather 1 plus I, here you get I. 1 minus I, you get minus I. So the given problem becomes 1 plus I upon 1 minus I whole power m equal to 1. This takes the form I power m equal to 1. Now m must be a positive integer, rather m belongs to n, natural numbers 1, 2, 3. So when m equal to 1, I power 1 is 1, I power 1 is I square is minus 1, I cube is minus I, and I power 4 is plus 1. So the least value for which I power m becomes 1 is 4. So m equal to 4. Third option is the answer. Before the next problem, we shall define locus of a point and its equation. The locus of a point is the path traced by a moving point, px, y, which moves in a plane under certain geometrical condition or conditions. You can have more than one condition. The relation between the coordinates x and y of an arbitrary point px, y is expressed in terms of an equation called equation of the locus. Let C be a fixed point in the plane and P be an arbitrary point or moving point which moves in a plane such that its distance from the fixed point C remains constant. Clearly, the path traced by the point P is a circle. this distance remains constant is the radius of the circle, and the point C is the center of the circle. You take any point on the circle, its distance from the point C remains same. That is again radius. If Z1 and Z2 are two complex numbers, then modulus of Z1 minus Z2 gives us the distance between the 2 points representing the complex numbers Z1 and Z2. Now, if C represents the complex number Z0 and P, arbitrary point P, represents the complex number X plus IY, then Z minus Z0 always remains same, that is R. Therefore, this gives the equation of a circle of radius R with the center at C. Therefore, the equation modulus of Z minus Z0 equal to R always represent a circle of radius R with the center at Z0. In the same way, you can remember the equation modulus of Z minus Z1 plus modulus of Z minus Z2 equal to constant K always represents an ellipse with foci Z1, Z2 with the center at 0, 0, provided modulus of Z1 minus Z2 is less than K. That is, distance between these two foci must be less than K, the constant. Further, the constant K is nothing but the length of the major axis. Similarly, the equation modulus of Z minus Z1 minus modulus of Z minus Z2 equal to K represent a hyperbola with foci Z1 and Z2, provided the distance between Z1 and Z2 should be greater than the constant K, what you have K here. Further, K is nothing but length of the transverse axis. It is easy to remember because the Cartesian equation of the ellipse is x square upon a square plus y square upon b square equal to 1. So here you have a plus sign, so is here. The Cartesian equation of a hyperbola is x square by a square minus y square by b square equal to 1. So here you have a negative sign, so is here. Easy to remember. The third result is the equation modulus of Z minus Z1 upon Z minus Z2 equal to constant K, which can also be written as modulus of Z minus Z1 equal to K times modulus of Z minus Z2. This always represent a circle provided the value of K is not 1. Suppose if K is 1, then the equation reduces to Z minus Z1 under modulus equal to modulus of Z minus Z2. So which gives us, or which represents, the perpendicular bisector of the line joining the points Z1 and Z2. Question number 8. If 1 minus I upon 1 plus I whole power 96 is A plus IB, then we need to find values of A and B, that is A comma B. 1 minus I upon 1 plus I whole power 96 is A plus IB. I have mentioned in the earlier problem, 1 minus I upon 1 plus I simplifies to minus I. So you can write this as minus I whole power 96 equal to A plus IB. Further, minus I whole power 4 whole raised to the power 24 is A plus IB. As we know, I power 4 is 1. Minus I whole power 4 is also 1. You can write this as 1 power 24, that is A plus IB. 1 power 24 is 1 plus, no harm if I write plus I times 0, A plus IB. Now equating the corresponding real and imaginary parts, you get A equal to 1, B equal to 0. Therefore, A comma B is 1 comma 0. So the answer is second option. Ninth one, if alpha and beta are the roots of this equation, then we need to find alpha square plus beta square. So given that x square plus x plus 1 equal to 0, you can compare this with a quadratic equation and find the coefficients a, b and c, and then write the sum of the roots, product of the roots, just like in the earlier problem. Instead, if you look at this equation very closely, so this is very similar to the result, known result, omega square plus omega plus 1 equal to 0, where omega is a cube root of unity. So therefore, omega is a root of this equation 1. So omega is a complex number. Complex roots, if any, of any equation always occur in conjugate pairs. Means that if 2 plus I3 is a root of the equation, then its conjugate 2 minus I3 is also a root of the same equation. So now omega is the root of equation 1. Its conjugate, that is omega bar, is omega square, is also a root of 1. So therefore, the two roots alpha and beta are omega and omega square. Now we shall find value of alpha square plus beta square, that is omega square plus square of omega square, that is omega square plus omega power 4, omega square plus, you can write it as omega cube into omega, that is omega square plus omega, because value of omega cube is 1. Further, this omega square plus omega equal to 1. Therefore, this becomes minus 1. So the correct answer is option 4. Question number 10. If z is x plus iy, then the equation represent equation of this form always represent a straight line. We have already discussed that. So here there are two straight lines, y-axis and x-axis. Now let us find out what does it represent. Modulus of z plus 1 equal to modulus of z minus 1. You can write this as z minus of minus 1 equal to z minus of z minus 1. This is of the form modulus of z minus z1 equal to modulus of z minus z2. So this represents a perpendicular bisector of the line segment joining the points representing the complex numbers z1 and z2. So the 2 points are now z1 corresponds to minus 1, minus 1 comma 0, and z2 corresponds to 1 comma 0. So that is minus 1 comma 0, and this is 1 comma 0, x-axis, y-axis. So the perpendicular bisector of this line segment AB is nothing but y-axis. So the answer is first option, y-axis. Eleventh one, if 1 plus I upon 1 minus I whole power x equal to 1, then x satisfies the equation x equal to 4n plus 1 or 2n plus 1 or 2n or 4n. It's given that 1 plus I on 1 minus I whole power x equal to 1. As before, we shall directly take 1 plus I upon 1 minus I as I. That is I power x equal to 1. So we know that the least positive integer for which I power x is 1 is 4. So I power 4 is 1. Now, raising both sides to the power, any integer or any natural number I power 4 whole power n equal to 1 power n, where n belongs to natural number. So you get I power 4n equal to 1. Compare equation 1 and this equation 2. So that gives us x equal to 4n, where n belongs to set of natural numbers n. So the option is fourth option. So this is very simple. So in the given expression, you have values . 12th problem. It's very simple. Given 3x plus I times 4x minus y equal to 6 minus I. You can write this as 6 plus I times minus 1. Now equate the corresponding real and imaginary parts. Whenever two complex numbers are equal, their real parts are equal and also their imaginary parts are equal. Only then two complex numbers are equal. So 3x equal to 6, x is 2. Equating the imaginary parts, 4x minus y equal to minus 1. We shall take the value of x, that is 4 times 2 minus y equal to minus 1. So 8 plus 1 equal to y. Therefore, y is 9. So the values of x and y are respectively 2 and 9. So the correct option is option 4.